Derivative matrices on a staggered grid. We have a bit of work to do in this video, and we are going to build 4 separate derivative matrices. 2 of them are calculating derivatives with respect to x, and 2 of them are calculating derivatives with respect to y. But we also have 2 different functions. We have f and we have g, and they are staggered on this 2-dimensional grid. And we've already seen how when we stagger functions, that changes the derivative matrices a bit. Now we want to talk about staggered grids, staggered 2-dimensional grids, and what those derivative matrices look like. So we'll do that, and we'll end with some final notes. Right-handed derivative matrix DXF. So we have a 3x3 grid, and we would like to build a derivative matrix that calculates a derivative with respect to x, so it's in the x direction, of the f function. And so I'm drawing the grid with the f function here. The finite difference approximation that we're using is right here. And notice we're not using the first order derivative approximation that has a 2 delta x in the denominator. It's a single delta x. That means we're using adjacent f values, and so the finite difference ends up right at the midpoint, and of course that leads to the staggering, and we'll place the g function at the midpoints of the f and the f at the midpoints of g. So we want to go point by point, all 9 points on this grid, and write this finite difference approximation. And so we'll end up with a set of 9 equations. Here are those 9 equations. We'll take one at a time. We'll draw that on the grid and explain what's happening and how we can write that finite difference approximation. So we are looking at our first finite difference equation, and the red arrow is telling us, pointing to where the derivative is being calculated. So we're looking at the difference between these 2 function values, dividing by the space between them, and that's calculating the first order derivative at the midpoint, assuming we're interpreting that as a central finite difference, which we are. So the red arrow points to where the derivative is being evaluated, and the red box encompasses the points from which we're calculating the finite difference, and we're also highlighting the finite difference approximation that is specific to this point. So let's begin. The first point, we are calculating the first order derivative at the midpoint, and if we go with our equation at the bottom for our finite difference, it's the function from the next cell over in the x direction minus the function from the same cell divided by the spacing delta x. So both f11 and where we're evaluating the derivative are in the same cell. So it's the f21 that's actually from the next cell. Plus it's in the positive x direction, so it makes sense that it's f21 minus f11 divided by the spacing between them, which is delta x. So we have an f21 minus an f11 divided by delta x. No boundary condition problems here. Even though we're at the left side of the grid, no boundary condition problems. Let's move to the next finite difference. We're calculating the first order derivative with respect to f, and that will exist right here at this point. And so the finite difference approximation will be f31 minus f21 divided by the spacing between them, delta x. f31 minus f21 divided by delta x. Let's move to the next point. Here, we're evaluating a derivative that's from outside of the grid. This means we're going to need a function value from even farther outside of the grid. So it would be this function value from outside the grid minus f31 divided by the spacing between them, which is delta x. Now we don't have this function value from outside of the grid. Here we're going to be applying simple Dirichlet boundary conditions. And that means any function value from outside of the grid, we'll just let be 0. So our finite difference expression would then be 0 minus f31 divided by the spacing delta x. 0 minus f31 divided by delta x. Let's move on to the next point. We're in the next row, No boundary condition problems here. We're evaluating our first order derivative right at the midpoint between f12 and f22. So the finite difference approximation would be f22 minus f12 divided by the spacing between them, which is delta x. So it's f22 minus f12 divided by delta x. Next point. No boundary condition problems here. So the finite difference approximation is f32 minus f22 divided by the spacing between them, that's delta x. f32 minus f22 divided by delta x. Let's move on to the next point. Here we're evaluating a derivative from outside of the grid. We have a boundary condition problem because we need a function value to the right of where we're evaluating the derivative, and that does not exist. Following the Dirichlet boundary conditions, we'll just set that equal to 0. So our finite difference approximation is this function value from outside the grid, 0 minus f32 divided by the spacing between them, delta x. 0 minus f32 divided by delta x. Next point, no boundary condition problem here. And so the finite difference reads f23 minus f13 divided by the spacing between them, delta x. f23 minus f13 divided by delta x. Next point. Here we're evaluating the finite difference at the midpoint between f23 and f33. So the finite difference approximation would be f33 minus f23 divided by the spacing between them. f33 minus f23 divided by the space between them, delta x. And the very last point, which we're evaluating the derivative outside of the grid. So it needs a function value from outside of the grid. That does not exist. We will follow our Dirichlet boundary conditions and just set that equal to 0. So our finite difference approximation would then be 0 minus f33 divided by the spacing between those points, delta x. 0 minus f33 divided by the spacing between them, delta x. I'll point out one other thing. Notice the boundary condition problems only happen at one side of the grid. When we were talking about co-located grids, we had boundary condition problems at both sides. Here it only occurs at one side. And it will turn out when we look at derivatives for G, the boundary condition problem will still only happen at one side of the grid, but it will be the other side of the grid. So they have asymmetric boundary condition problems. So here we are with our 9 equations, and we would like to put those into matrix form so that we can come up with this derivative matrix that'll calculate derivatives of f, first order derivatives of f, with respect to x. Notice all of these terms are being divided by delta x, so I just brought the 1 over delta x to the outside of this column vector and also to the outside of this matrix. But make no mistake, we really do need to divide all the elements in the matrix by delta x and all the elements in the column vector by delta x. So in order to figure out the derivative matrix, we write this big blank matrix equation, and we ask the question, what needs to go in this matrix such that when we pre-multiply this column vector of our unknown functions, we get the answer over here. And I've essentially written all the numerators from our equations on the right and put them into this column vector, and that's because the 1 over delta x is to the outside. So I can read off these f's, and we can figure out what needs to go in that big matrix. Here's what it is. We don't have a symmetric matrix anymore like we did for co-located grids. We have negative ones going down the center diagonal. We have mostly positive ones going up that upper diagonal and just all zeros in the lower diagonal. We will notice that we have 2 1s and a 0, 2 1s and a 0, and then 2 1s. And these zeros mixed in there, this is the boundary conditions that we came across. And since we were rastering first along x, we kept hitting a boundary condition, going back, hitting another one, going back and hitting another one. And so the zeros are sort of dispersed out there. So that is our derivative matrix. For the function f, we should only apply that to the function f, and it calculates a first order derivative with respect to x and evaluates those derivatives at the midpoints between the f values. Let's take a closer look at the anatomy because this gives us some clues on how we can build this very quickly. The center diagonal is all -1s, so that's easy. Just insert all -1s down the center diagonal. The upper diagonal is mostly 1s, but there's zeros in a few spots. That's due to our Dirichlet boundary conditions. And if we notice, they are nx number of points apart, where nx is the size of our grid horizontally. And so how many zeros do we have? Well, we'll be missing the last row of our grid. But if we have 10 rows, we're going to have 9 zeros, and the spacing between them will be the number of points horizontally in that grid. So we can use those, and now we know how to build that matrix very quickly. Right-handed derivative matrix, DYF. Here we're still calculating derivatives of the f function, but this is with respect to y. So we're taking derivatives in the vertical direction now. The finite difference equation that we're basing it off of is essentially the same thing for our derivative with respect to x that we just did, but it's in the y direction. So you notice there's a j plus 1 and a j. So it's still function from the next cell in the y direction minus the function from the same cell. So what we want to do is write this finite difference equation for every single point on the grid. When we do that, we get 9 separate equations. What we will do is go through each of these one at a time, draw that on the grid so we know what's happening. We know the position where the derivative is being evaluated. We know which function values are being used to evaluate that, and we can see that for every single equation. So let's go ahead and get into this. The very first finite difference equation, the blue arrow here identifies the point where that derivative is being calculated. And so if it's a central finite difference, it's being calculated at the midpoint between two function values. And notice this is vertically now because the derivative is with respect to y, which is up and down for us. So the blue highlight here is bounding the points that we're using to calculate the finite difference at the midpoint. And also the highlight over here shows the finite difference equation written specifically for that point. So here we go. How does this finite difference work? There's no boundary condition problems, right? Because we're spanning all the points that we need for the derivative right here. And so we would have the function value at the next cell down, which is f12, minus the function from the same cell, divided by the spacing, which is delta y. So let's come over here, and we have f12 minus f11 divided by the spacing, delta y. Let's move to the next point. We're evaluating the derivative at the midpoint between f22 and f21. So the finite difference approximation would be f22 minus f21 divided by the spacing between those points, which is delta y. So we have f22 minus f21 divided by the spacing between those points. Next point. We're evaluating the derivative with respect to y at the midpoint between f32 and f31. So the finite difference approximation is f32 minus f31 divided by the spacing between them, delta y. f32 minus f31 divided by delta y. Now we move down in the grid. Still no boundary condition problems because we're calculating the derivative at the midpoint between f13 and f12, and our window's spanning 2 points, so we have all the function values that we need. So the derivative at this midpoint is f13 minus f12 divided by the spacing between them, which is delta y, f13 minus f12 divided by delta y. Next point. No boundary condition problems. Looks like an easy one. Our finite difference approximation will be F23 minus F22 divided by the spacing between them, which is delta y. F23 minus F22 divided by the spacing between them, which is delta y. Next point, still no boundary condition problems. Our finite difference approximation will be F33 minus F32 divided by the spacing between them, which is delta y. F33 minus F32 divided by delta y. Next point. Now we have a boundary condition problem. We are evaluating the derivative outside of the grid. And so if this is going to be a central finite difference and F13 is one of those terms, we need to reach over and below where we're evaluating the derivative. We need a function value from right here, which is not being stored, that does not exist. We've said that we're applying Dirichlet boundary conditions here, so we will assume everything outside of the grid is 0. That means our finite difference approximation will be written as this field value outside the grid, which is 0, minus F13 divided by the spacing between them, which is delta y. So we have 0 minus F13 divided by delta y. Next point, we still have a boundary condition problem. And so we're calculating the finite difference a little bit below F23. And if that's a central finite difference, we need to reach symmetrically to the other side of it. There is no field value down here. So again, following Dirichlet boundary conditions, our finite difference approximation will be 0 minus F23 divided by the spacing between them, delta y. 0 minus F23 divided by delta y. And the very last finite difference approximation has, again, a boundary condition problem. It needs an F value symmetrically underneath it, and that doesn't exist. It's outside of the grid. Following Dirichlet boundary conditions, we'll let that be 0. Now our finite difference approximation reads 0 minus F33 divided by the spacing between them, delta y. 0 minus F33 divided by delta y. So we've gone through each one of these and we've developed a set of 9 equations. We can then cast these equations into matrix form to figure out what our derivative matrix looks like for calculating first order derivatives of f with respect to y. Notice on the right-hand side of these equations, all of these terms are being divided by delta y. So I'm dividing by delta y. So in this column vector, I'm just seeing the numerators essentially. And I bring the 1 over delta y of this matrix. So we have this big blank matrix that is pre-multiplying all of our unknown function values. It's a column vector containing the unknown function values. And that has to equal our finite difference approximations. So what goes in here to give us that? And we see we have something with 2 diagonals again. We have negative ones going down the center diagonal, and we have positive ones going down an upper diagonal, but there's no zeros mixed in with this. For derivatives in the y direction, because we're rastering first along x and then along y, just inserting 2 pure diagonals, we have Dirichlet boundary conditions already there. So derivatives in the y direction are much easier to construct than derivatives in the x direction because of those boundary conditions. So this matrix, along with dividing by delta y, is our first order derivative matrix of the function f with respect to y. Let's quickly discuss the anatomy of this derivative matrix because this will give us a clue how to build this very quickly. We know we have to insert 2 diagonals. We know these negative ones are going down the center diagonal, but where are these positive ones? Well, we move over a distance big NX. That's the number of points wide our grid is. Given that, we know where to insert these positive ones. And we don't have to do anything else for boundary conditions, just 2 pure diagonals. And then, of course, divide by delta y. Don't forget that. And we'll have our derivative matrix. Left-handed derivative matrix dxg. Here, we are calculating a derivative with respect to x, but now of a function g. And the staggering for f and g is different. And we can see that in the finite difference equation that we're using. Remember what it was for f. It was f from the next cell minus f from the current cell. Now, if we look at our finite difference for g, it's g in the same cell minus g from the previous cell. And that's accounting for the staggering. So this is the finite difference approximation we'll use for g. It's being called a left-handed derivative matrix because we're reaching to the left in order to calculate the finite differences, whereas the derivatives of f were right-handed because we were reaching to the right, to the next cell. Here we're reaching to the previous. So what we want to do is write this finite difference equation for every single cell on our grid. And we have 9 cells, so we'll get 9 equations. Here are those 9 equations. What we'll do now is we will go one at a time. We will draw the finite difference approximation on the grid, talk about how that's happening, and also highlight the specific finite difference approximation for that cell on the grid over to the right. So let's get into this. For the first cell, because these are left-handed derivative matrices, we are evaluating the derivative to the left of G1. And so if we're interpreting this as a central finite difference, we need a G symmetrically on the other side of it. But that G does not exist. That is outside of the grid. This green highlight is highlighting the terms that we're using, the points that we're using to calculate the finite difference at the midpoint. But this G, I guess it would be a 0, 1, but that doesn't exist. And so we're going to use Dirichlet boundary conditions where we assume all functions from outside the grid are 0. So that's exactly what we do. So now the finite difference will read G11 minus this G from outside of the grid, which does not exist, so we'll just let it be 0. So G11 minus 0 divided by the spacing between them, which is delta x. So our finite difference approximation is G11 minus 0 divided by delta x. Also notice here, we're having a boundary condition problem on the left side of the grid. Our f functions had their boundary condition problems on the right-hand side of the grid. Those were right-handed derivatives. We have left-handed derivatives. Our boundary condition problems happen to the left. Let's go to the next cell. So we're in the next cell, and no boundary condition problems here, so this is pretty easy. Our finite difference approximation will be G21 minus G11 divided by the spacing between them, delta x. G21 minus G11 divided by delta x. Let's go to the next cell. No boundary condition problems here. We're calculating the first order derivative with respect to x right here at the midpoint between these two g values. So the finite difference approximation would read G31 minus G21 divided by delta x, which is the spacing between them. G31 minus G21 divided by delta x. That's it for that row. Now we're in the next row all the way to the left, and we have our boundary condition problem again. We really need a G02, but that does not exist. We'll let that be 0. So our finite difference approximation now reads G12 minus 0 divided by delta x. G12 minus 0 divided by delta x. And that's, of course, calculating the derivative at the midpoint between this point that doesn't exist and G12. And that's right here where the green arrow is pointing to. Next cell. No boundary condition problems here, so this is an easy one. It's G22 minus G12 divided by the spacing between them, which is delta x. G22 minus G12 divided by delta x. No boundary condition problems here, so this is a pretty easy finite difference to write. and it's G32 minus G22 divided by the spacing between them, delta x. G32 minus G22 divided by delta x. Now we've come to our last row of cells. We're at the far left cell, and we're evaluating the derivative from outside of the grid to the left. And so we get the finite difference from G13 and the G that is out here but does not exist. It's outside of the grid, so we will let it be 0. And that evaluates the derivative right here. So that finite difference approximation would be G13 minus 0, because this is outside of the grid, we're using Dirichlet boundary conditions, divided by delta x, the spacing between them. G13 minus 0 divided by delta x. Next cell over, no boundary condition problem, so this one's pretty easy. G23 minus G13 divided by the spacing between them, delta x, and it's a central finite difference, so we're evaluating the derivative right here at the midpoint. G23 minus G13 divided by delta x. And finally, the last cell, no boundary condition problems, so another pretty easy one. It will be G33 minus G23 divided by the spacing between them, delta x. G33 minus G23 divided by delta x. So we went one at a time through all 9 points on the grid and wrote 9 finite difference approximations. Now it's time to put these into matrix form so that we can figure out what our derivative matrix looks like. This is a first order derivative matrix of G with respect to x. So I write a big blank matrix equation, and we need to figure out what goes in here such that when we pre-multiply our column vector of unknown function values, our g's, we get our finite differences over here. Now every single term here is being divided by delta x, and I don't want to keep writing that, so I'm pulling the 1 over delta x out of this column vector, and I'm also pulling the 1 over delta x out of this matrix here. So what goes in that matrix to do this? Here's what that looks like. We have positive ones going down the center diagonal, and that's a pure diagonal. There's no zeros interspersed anywhere. Negative ones going down the lower diagonal, but there's some zeros here, and that was due to the Dirichlet boundary conditions. So we can imagine inserting 2 diagonals and then having to come back and figure out where we've goofed. If we just put negative ones everywhere, we have to go correct all of those different points where we shouldn't have put a -1 in there. But anyway, this is our derivative matrix, our first order derivative of G with respect to x, and don't forget to divide by delta x. Quick comment on the anatomy of this derivative matrix that'll help build it much more quickly. The center diagonal is all 1, so nothing really magical there. The lower diagonal, which has negative ones, has zeros put in here because of the Dirichlet boundary conditions. They are big NX apart, where big NX is the number of cells wide our grid is. So literally every NX, this would normally be a much bigger matrix, every NX, we need to put in a 0. Left-handed derivative matrix, DGY. So we have a 3x3 grid, the same one we've been working with. And here is our finite difference approximation for G in the Y direction. So now we're not taking derivatives horizontally. These are derivatives in the vertical direction. But it still has the theme of G from the same cell minus G from the previous cell. It's just now it's the previous cell in the Y direction. And then, of course, divided by the spacing delta Y. So this is our basic finite difference equation. We're going to write that for every single cell in this grid and come up with a set of 9 equations. Here's those 9 equations. The next thing we'll do is go one at a time. We will draw the finite difference on top of our grid and also highlight the equation that that corresponds to. Let's go ahead. So we start at the first cell. This is a left-handed derivative, so In this case, the left-handed side is really upward. It made more sense, I guess, for horizontal, but now we're talking about vertical. This arrow is pointing to where we want to evaluate the derivative, and it's always at the midpoint between two g values. Well, this is one of the values because this golden block here is highlighting all of the g values that we're using to evaluate the finite difference. We need to reach symmetrically to the other side of this arrow, and we need the g value from right here, which does not exist. If it did, it'd be a g10. So we're going to use Dirichlet boundary conditions and assume everything outside the grid is 0. That means our finite difference approximation is going to be G11 minus this value from outside the grid, which is 0. So G11 minus 0 divided by the spacing between those points, which is delta y. And here's our finite difference approximation, G11 minus 0 divided by delta y. Let's move to the second cell. We still have a boundary condition problem here because our finite difference is being evaluated above the grid and we need a value from even farther outside of the grid. That doesn't exist. We assume it's 0. And now our finite difference approximation reads G21 minus 0, the field value from outside, divided by the spacing between those points, delta y. G21 minus 0 divided by delta y. We move over to the next cell. We have another boundary condition problem because we're still evaluating derivatives above the grid, and the value of g we need is from even farther outside. So our finite difference approximation would read G31 minus 0, because we're using Dirichlet boundary conditions, divided by the spacing, delta y. G31 minus 0 divided by delta y. Let's move to our next cell. Now we're evaluating the derivative right here between these two g values, and the gold box is highlighting where we're the points from which we're calculating our finite difference. So our finite difference approximation will be G12 minus G11 divided by the spacing between them, which is delta y. G12 minus G11 divided by delta y. Next cell. No boundary condition problems here. This is a relatively easy one. And our finite difference approximation is going to be G22 minus G21 divided by the spacing between them, which is delta y. G22 minus G21 divided by delta y. Next cell, another easy one, no boundary condition problems, and our finite difference approximation is going to be G32 minus G31 divided by the spacing between them, which is delta y. G32 minus G31 divided by delta y. Next cell, still no boundary condition problems, another easy finite difference to write. G13 divided by G12 divided by the spacing between them, delta y. And that evaluates our first order derivative with respect to y right here at the midpoint. G13 minus G12 divided by the spacing, delta y. Next cell, another easy one, no boundary condition problems. We're evaluating our derivative at the midpoint between G23 and G22. So our finite difference approximation is G23 minus G22 divided by the spacing between them, which is delta y. G23 minus G22 divided by delta y. Last cell on the grid, another easy one because there's no boundary condition problems. G33 minus G32 divided by the spacing between them, which is delta y, and it's evaluating the derivative right here at the midpoint. G33 minus G32 divided by the spacing delta y. So we've gone one cell at a time, And we wrote our finite difference equation once for each cell, and we ended up with 9 equations. Now let's put that into matrix form so we can figure out what this derivative matrix looks like for calculating derivatives of g with respect to y. So I like to write a big blank matrix that pre-multiplies my column vector of unknowns g equals, and then I fill in a column vector of the answer that I want to get. And of course, these answers come from the finite differences that we've written on the right side over here. Now notice everything's being divided by delta y, so I don't want to keep writing that. I pull over my 1 to the delta y outside this column vector. Make no mistake, we really do need to divide everything in here by delta y. Likewise, I'm pulling the 1 over delta y outside of the big matrix here. Now we're in a good position to go ahead and fill in the elements of this matrix such that we get this answer on the right. And here's what that looks like. We have positive 1s going down the diagonal, and we have negative 1s going down the lower diagonal. Notice this is not interspersed with zeros anywhere. These are just 2 pure diagonals. Again, the y derivative, when we're rastering first along x and then along y, is a much easier derivative. Just inserting 2 diagonals defaults us to Dirichlet boundary conditions. The only thing we need to remember to do is divide by delta y. So what we end up with is our derivative matrix for the g function with respect to y. Let's talk about the anatomy of this derivative matrix because this will help us build it quicker. So we have 1s going down the center diagonal. That's very easy. And negative 1s going down a lower diagonal. Which lower diagonal is this? Well, it's the nx cells down. And so that tells us where to place these. And we don't have to interspace with any zeros. So that is a very easy derivative matrix to build. Final notes on these derivative matrices for staggered grids. Here is a summary of the anatomy of all 4 of these derivative matrices that we have built so far. I won't repeat the information that's here, but it's here in one slide, so you have it in one place. Here are some examples. We worked through a 3x3 grid. What if we had a 4x4? Well, here's what our 4 derivative matrices would look like for that case. Our derivative matrices have a relation, and it's related to the transpose and more specifically the Hermitian transpose. If we remember what a transpose operation is, we're essentially flipping a matrix about its diagonal. So we identify its diagonal and then just swap all of the off-diagonal elements symmetrically. That's a transpose. The Hermitian transpose is first a transpose, so you do that first, and then take the complex conjugate of everything. Now it turns out our derivative matrices are related. And we can calculate the derivative matrices of G straight from the derivative matrices of F. It's the negative Hermitian transpose. What's cool about this is we only have to build the derivative matrices for F, and then we can just directly calculate the derivative matrices for G. That's really cool and really useful. Now, I will mention this holds for most boundary conditions. However, there are boundary conditions where this fails. Newman boundary conditions, for example, this is not a valid thing to do, in which case we have to then go in and just build dgx and dgy, just like we did dfx and dfy. But for Dirichlet boundary conditions and periodic boundary conditions, this works fine, and I highly recommend doing it this way unless you have one of those types of boundary conditions that causes this problem, like Newman. So some rules that we have to follow when we build these. We have to look for the special case when the size of our grid is 1. So if the size of our grid is 1 in the x direction, that means we have like a toothpick kind of size grid. It may be tall in the y direction, but only 1 cell in the x direction. That doesn't actually mean we're simulating something very thin in the x direction. Actually, the opposite is true. That means it's of infinite extent in the x direction and perfectly uniform in the x direction. Nothing's changing in the x direction. If nothing's changing in the x direction, any derivative that happens has to be 0 if that derivative is in the x direction. So both dfx and dgx are both all zeros. And we have to check for this explicitly. So we'll check that. If this is the case, we set those derivatives all to zeros. Otherwise, we go and do everything it takes to build our matrices. We do almost the same thing for the y direction. If the size of the grid is 1 in the y direction, so we kind of have a horizontal toothpick grid, what that means is the thing we're simulating is of infinite extent in the y direction and uniform, and nothing changes. And if nothing changes, then any sort of y derivative should be 0. So dfy and dgy are all zeros matrix. So we need to check for that explicitly. If that's not the case, then we go ahead and do everything we need to do to build those matrices. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.